I'm very excited, very pleased to be back here. And I look forward to talking to some people who I haven't talked to in many, many years. And I'll tell you today something that was motivated by Hurricane Sandy in 2012, October 2012. So I'll jump right on to the main message of the presentation. The main message is that that storm surges can get the wiggle. So look at the screen very carefully because the storm surges can get the wiggle. So keep that in mind because that's the main message of the talk. And as I was saying, this work was motivated by Sandy in late October of 2012, which was predicted to be a superstorm. I don't need to tell you all of this. I'm sure that you've heard a lot about it, but it was caused by the fact that we had a low pressure system moving eastward from Western Canada that coincided with a low pressure system running in the North Atlantic there. And you had the Hurricane Sandy also appearing in southeast Florida there. And we know that the fusion of two low pressure systems creates a much more powerful low pressure system. That's what's called the Fujiwara effect. But in this particular case of Sandy, we had the fusion of three low pressure systems. So we had a double Fujiwara effect. So that was a super storm, as they called it. And indeed, it met the expectations. It was the second costliest Atlantic hurricane. It caused the largest storm surge at Battery Park on record. It caused the highest wave on record in New York Harbor, recorded up to 10 meters. It caused the second lowest barometric pressure north of Cape Hatteras. And it became the largest hurricane on record for Atlantic. And as you see on the image there, the winds were spanning a huge diameter to 1,500 kilometers. So the effects of the storm were pretty widespread. Incidentally, this happened while I was on sabbatical in Spain, so I was very worried about what was happening in the eastern US. And I was following, I live in Florida, so I was following what was happening in Florida. And I realized that this was going to affect the entire eastern coast of the US, so that made me look for data and follow what was happening. So the interesting aspect of Sandy was its track, as you see here in the red line, that as I was saying, it affected practically the entire eastern seaboard of the US. It followed the coastline pretty much in a parallel fashion from south of South Florida to Cape Hatteras in North Carolina. And then once it went past to the mid-Atlantic bight, it sort of made a left turn and went directly to the coast. And we know that when a low pressure system crosses a bathymetric step, like the continental shelf here, like the shelf break, sorry, when it crosses, when a low atmospheric pressure system crosses a step, it causes a perturbation in the water, right? And that perturbation has been studied in many different papers throughout the years, starting in the 50s, and that's still a fashionable topic to study. We know that crossing of a perturbation across a step causes waves that can propagate either to the north or to the south, both in the mid-Atlantic bight and the South Atlantic bight, as shown here in this arrow. And they are called different names, and they range in periods from a few hours to a few days, like the edge waves, subinertial waves, Kelvin waves, and double Kelvin waves. And so this was an opportunity to see whether we can follow any of these types of waves. As it turns out, we couldn't identify any of these, but we identified something else, which is the main message of the talk. Remember that the surges can get the wiggle. But particularly these waves are like teenagers, right? They're free, transient and free. And what that means is that once they're forced, they propagate without any other forcing, and they dissipate eventually. They're transient and free. And which contrasts to the wiggles that I'm going to be talking about. But that was fortuitous, what we found out. So again, I was curious to see what was happening in the eastern seaboard, as we saw from afar that this storm was going to affect the entire eastern seaboard. So we looked at stations from Tides and Currents. It's a great resource by NOAA. And sometimes we talk about badly, we talk badly about the government, but I think this is a wonderful resource that the government provides. And we have data throughout all those yellow dots that you see throughout the eastern seaboard of the US. So I started collecting all those data and seeing what was happening. So I looked at wind velocity, barometric pressure, predicted tide, and observed tide. And the first thing that we noticed, if we plot all the data, this is all the data from the eastern seaboard. So on this axis, the vertical axis, we have distance from Miami. And in the horizontal axis, we have time in days in October. So this is what's called a Homeowner Diagram, or a phase diagram. It's used very often in atmospheric sciences and in oceanography to describe propagation of signals. So what you see two variables here. The arrows represent the wind velocity, denoting where it's going to. And the color referred to that color bar up there is the atmospheric pressure in hectopascal. So two things to note with respect to the color distribution, which is the atmospheric pressure. So, well, first of all, let's try to understand what we're looking at. For those of you who are not familiar with Homeowner Diagram. So what we see here is what's happening at any given time throughout the eastern seaboard. So for example, these darkest area is the lowest atmospheric pressure, and that's around 940 hectopascals, and that occurred right off of Atlantic City right around October 30th. So that's what this graph is telling us. So two things to note is obviously the presence of the low atmospheric pressure from the hurricane, that it dropped like 80 hectopascals, right, from 940 to 1020, 80 hectopascals. Just from the inverse barometer effect, one would have expected that the storm surge produced by that inverse barometer effect would have been 80 centimeters, just from the pure barometric pressure. So that's one thing. The other very curious thing, and it's very subtle, is this banding of atmospheric pressure signal. So that's a semidiurnal oscillation of around 1 to 2 hectopascals, and that's the natural atmospheric tide that you observe. So I bring this up because this might be related to the wiggles that I'm going to be talking about later, but it might not be. I'll explain that. All right, so those are the two main things that I want to talk about with respect to the atmospheric pressure, these semidiurnal oscillations of atmospheric pressure and the drop in atmospheric pressure. Now let's look at the wind, which are the arrows. Remember, the wind is the arrows are pointing in the direction in which the wind is blowing. So mostly from the northeast toward the southwest throughout most of the time and throughout most of the eastern seaboard. Right? So that's what you would expect from a low atmospheric pressure. Just as reference, I have the names of the stations here on the right so that you can sort of position yourself with respect to the vertical axis. All right, so this is sort of a background information. It doesn't really pertain to the storm surge. When we looked at the surge, this is what we observed. When we looked at one station right at the border between Florida and Georgia, which the station is called Fernandina Beach. If you have never been there, it's a beautiful place to visit. For those honeymooners, probably you never heard of this place, but it might be a place to consider. And this is what happened. In the horizontal axis, we go from October 25th to October 30th, and we have three lines here. The first one I want you to look at is the blue one, which is the predicted tide. That's what we expected the tide to have looked like. And then the green one is what actually looked like. It's the observed tide. So you see a difference, right? A surge there. That is the green line is higher than the blue one. But when you do the difference between the two, which the observed minus predicted, we'll call the surge or residual tide, that's the purple line. And this is what caught our attention initially. What's going on here? At this particular location, you have these semidiurnal perturbations to the surge, as I've called them, or these are semidiurnal oscillations of the surge. And we said, is this a fluke? Are these real? What's going on here? Have these perturbations been described before? And they had been described before for the eastern coast of England, and I'll explain in a moment what they really are. But in order to see whether they were a fluke or not, then we looked at all the stations, and we plotted the surge for all the stations. So this is a Homeowner diagram, now represented sort of in a 3D sheet representation, if you want. Again, we have distance from Miami on this axis, we have time on this axis, and we have the elevation of the surge represented by this, what I would call a beautiful representation. Well, obviously, what can I say? But one thing that you definitely notice is that peak over there, right? That's a surge from Hurricane Sandy. Yeah? Sandy, right?
Yes.
But that's not what really caught our attention. What caught our attention were these perturbations, right? So I showed you only one of the stations here. This occurred practically throughout this South Atlantic bight from Cape Hatteras almost all the way down to Central Florida. And look, they occur over several days. And if you observe a little bit, even in the Mid-Atlantic bight, they can appear. But I'm going to concentrate mostly on the ones in the South Atlantic bight. If we look at them in a different representation, now this is the same Homeowner diagram. This is the same exactly representation, now in a flat sheet. Again, you see up there, that's a surge from Sandy. And what caught our attention were these perturbations. What I've done in this figure, I've also plotted this broken line. That broken line pretty much guides us through the peaks of these perturbations, how the signal propagated from around Cape Hatteras southward and even northward. The southward propagation was twice as fast as the northward propagation, which is an interesting fact that we're not able to explain yet, but we are exploring it. But the essence of this is that these perturbations occupy practically the entire South Atlantic bight, as shown there, right? So the question is, are these related in any way to the tides? And what we have here is a Homeowner diagram of the predicted tides for the entire eastern seaboard. Again, this is the same vertical axis versus time, and the colors show the predicted tide, so high tide, low tide, high tide, low tide. You see how the tidal signal propagates from Cape Hatteras southward, but also there's something funny between Miami and Central Florida here, and then the Mid-Atlantic bight, you see how the signal propagates, and then this is the tide inside Long Island Sound. That's why you see a large shift in the signal. And I've drawn the broken line. Those are the peaks that I showed in the previous graph, just to show that those semidiurnal perturbations that I was showing before, they're sort of related to the tide, but they're not tides, and they're not behaving like the tide exactly. They're emulating the tide, but not really. So when you compare the observed, when you compare the surge versus the tide, what you get is that this suggests that you have storm-tide interactions. All right, so that's where we start our investigation, that we need to understand these storm-tide interactions better to try to explain these semidiurnal perturbations a little better. So the first thing that we look at, since the perturbations amplify here in the South Atlantic bight, we look at the tidal chart of the South Atlantic bight, and this is what the tidal chart looks like. The continuous contours, the dark contours, are the co-phase lines. It tells us how the phase propagates. So what this shows is the tide propagates like this, almost very rapidly, only a few degrees difference. So this is 7 degrees, 9 degrees, so this is only 9 degrees, it's 18 minutes, right? 18 minutes from here to here for the tide to propagate. And interestingly, here in the South Atlantic bight, the tide sort of refracts and gets delayed, as you see here. The red dotted lines represent the amplitude of the tide. And you see that the amplitude is 0.5, and we're talking about semi-diurnal tides. 0.5 meters here amplifies to up to 1 meter. So what this is showing is simply that the tide propagates from north to south very rapidly. It diffracts a little bit in the South Atlantic bight, and it amplifies in the South Atlantic bight. When you compare that to the tidal currents, as represented by the tidal ellipses here, the tidal ellipses show that the tidal currents are very weak here, as you see by the dots. And these ellipses indicate that the currents rotate like that in an elliptic way. But you see how the currents amplify quite a bit, the tidal currents amplify quite a bit on the continental shelf, and they become oriented onshore, offshore. What's important here, and the main message of this figure, is that we have a 90 degrees phase lag between the elevation and the currents, and the tidal currents. So what this indicates is that we have a standing wave. The tide here behaves like a standing wave. And it practically, in the South Atlantic bight, it goes up and down in a direction perpendicular to the coast. So it's going like this, the tide is going only like this. All right, so that's going to be very important, because what we find out is by looking at a qualitative explanation of this, using some dynamical argument, is as follows. So here I'm going to ask you to bear with me, for those of you who haven't taken physical oceanography, but for those of you who have taken physical oceanography, you'll probably remember all this. So what we're assuming is that in the South Atlantic bight, you have a standing wave like drawn here. This wave that you see here can be considered as a standing wave, okay, just going up and down in time. And that standing wave can be represented with symbols like this. Two waves traveling in opposite directions. This is one wave traveling in one direction, a wave traveling in opposite directions. So the superposition of those two waves will produce a standing wave. Right? So that would be the regular situation when there's no hurricane in the South Atlantic bight. What we're proposing is that when there's a hurricane, before I go there, so this comes from this equation there that's called the wave equation, and it's simply a combination of a momentum balance and the mass balance in the system. And the momentum balance that is described in that equation simply says that the accelerations of the tide are produced by a pressure gradient. So that the accelerations are caused only by the water going like this. Right? That's what that funny looking equation tells us, simply, that the accelerations of the water are produced by the water going like this, simply. And what we're suggesting then is that when we have a hurricane, this gets modified. And this could get modified in different ways. So up to now, I've shown you this part of the equation. And the modifications that the hurricane can produce can be in different ways. This term represents the effects of the Earth's rotation. And I'm not going to go in many more details than saying that the Earth's rotation can modify the way that the standing tide can behave. And then we have three effects here. One produced by the surface wind, by the surface stress, by the wind. So the wind can modify the tide, really. So it's like an additional body force in addition to the tide. The tide can be modified by the barometric pressure, and the tide can be modified by bottom frictional effects. All right, so this was proposed in a paper in 2011. But what this, let's say, momentum balance does not consider is the nonlinear effects from geometry, or the advective effects. So, well, I'm getting ahead of myself. This equation can be synthesized or simplified in this way. So we have the wave equation that I showed before like this. And this term will include the effects of rotation, of surface friction, of bottom friction, and of atmospheric pressure. So those four effects can modify the tides. If we have a modification of the tides, then one of the two waves, the incident or the reflected, can have a phase lag, can get out of phase. And if we get out of phase, then we have that orange line that is drawn up there. Probably you can't even distinguish between the blue line and the orange line because the phase lag will be very small. But when we do the difference between the two, as I'll show in a moment, you see the difference, right? But there's no apparent difference from there. As I was saying before, what this momentum balance doesn't consider is the effects of advection. And in these two papers, they explain, actually, those were the ones who explain the appearance of these wiggles in the tides, but they explain it due to the effects of advection. They didn't include rotation. All right, so we have all those explanations. To make this a little more evident, I hope, when we compare the predicted tide, which is the blue line, versus something that you may observe, which is the orange line, and to the orange line, I've added some surge, that is the water level going up because of the surge. When you do the difference between the two, you get that red line. And that red line starts looking like the purple line. So this is sort of a conceptual explanation of what's going on. What we're suggesting these perturbations are, these semidiurnal perturbations, or this surge to the wiggle, is that an extra force is modifying the tide to cause a phase lag between the predicted and the observed. And it's simply the difference between the two that gives us the purple line. So physically what's happening is that the tide is getting delayed by the hurricane, right? That's the essence of the argument. And we can explain that qualitatively with dynamic arguments using this expression. But we don't know yet which forcing is the one that's causing the phase lag. We don't know yet. So what we need to do is we explore this with a numerical approach, with a numerical model over this domain, a good part of the Western Atlantic. There are the stations for which we have data. So this is a two-dimensional version of the regional ocean modeling system. So this solves the entire momentum equation in such a way that we can look at the different contributors to the momentum balance, the different forces that cause the accelerations that we observe, so that we are able to tease out what the mechanisms are that cause these semidiurnal perturbations. The model had a resolution of 5 kilometers, and it was forced with forecasts for winds, for atmospheric pressure, and for tides. And that's another very valuable service from NOAA, that they provide these forecasts, and we were able to use those forecasts to feed into the model and look at the effects of, and look at the hurricane, look at Sandy, all right? So again, why am I doing this? Because I want to find out what forces cause this phase lag between the observed and the predicted time. What caused the wiggles that I observed, all right? So we ran the model first under process-oriented conditions. In this case, I show the Homeowner Diagram of the results, forced by atmospheric pressure with no tides and no winds, just the atmospheric pressure. So what do you see? You see the storm surge appearing there as we observed, but we don't see the wiggles in the South Atlantic Bight, which would be around here. Now, when we have atmospheric pressure forcing plus tides, again, we see the surge of Sandy there, but we don't see the wiggles. So we can say from here that atmospheric pressure alone will not cause the wiggles. Right? When we have the model forced by the winds, but with no tides, we have some signals here, but no semidiurnal perturbations, so no wiggles when we force with the wind and no tide. When we have the combination of wind and tide, so storm and tide interactions, then we get the appearance of some wiggles there, kind of faint wiggles, but they appear. So this is an important ingredient we found out from this simulation. Then by combining atmospheric pressure, winds, and no tide, again, we have a perturbation here, but this is not semidiurnal, so this is not relevant. And what we find out, when we have the combination of the three, atmospheric pressure, wind, and tides, we get something that might look similar to, at least qualitatively look similar to what we observed. This is the Homeowner Diagram of this observed surge, and this is the simulated surge with atmospheric pressure, winds, and tides. All right, so these results indicate that we have storm-tide interactions, that the interaction between winds and tides are an essential ingredient to produce these semidiurnal perturbations. The next question is, okay, we have these interactions, what's the force that's causing the perturbations? Theoretical studies have shown that they can be caused by bottom friction or by nonlinear advection. Right? So we started with that hypothesis. Either of those two were going to be causing the perturbations. So we looked at the momentum balance at the point, at the station, where we get these perturbations of greatest amplitude. Remember where that was? That was at the border between Georgia and Florida. So we looked at that point in the model. We looked at the momentum balance in that point. So this is a busy slide. So first, look at the red line. We're looking at all the terms in the momentum balance. So look at the red line first. We have local accelerations, pressure gradient, advective accelerations, bottom stress, Coriolis acceleration, and wind stress. Remember, this model was running in two-dimensional form. So what do you see from this? By looking at the red line, you see three terms that dominate the tides only, right? The red line is only for tides. And this makes sense. We have local acceleration, pressure gradient, and Coriolis acceleration. What that simply means is that the pressure gradient, when the water level goes like this, the water will move like that and be modified by Coriolis. When the water level goes like that, the water will move in the opposite direction, modified by Coriolis. That's what this tells us, the red line tells us, okay? All right, so that's pretty simple, pretty straightforward. We didn't learn anything from that. Then let's look at the green line. The green line only, we see that the local accelerations are weak. The pressure gradient balanced by wind stress and Coriolis acceleration. Does that sound familiar to the physical oceanography student? You probably heard about Ekman dynamics. Well, that's sort of Ekman dynamics. We have the pressure gradient here too. Some people call it Ekman dynamics even with the pressure gradient, but it's something similar to Ekman dynamics, right? So when the wind blows, we have something similar to Ekman dynamics. That's what we learned from this simulation. Again, we didn't learn much from that. Where we learned something, and we were very surprised, is by looking at the blue line, which is the results of the interaction of the tides and the wind. Why do I say that? Because you see, local acceleration is important and pressure gradient is important. But what's the next term that's important? This is what surprised us. The Coriolis acceleration seems to be balancing the local acceleration pressure and pressure gradient. So what these simulations suggest is that Coriolis acceleration is causing the semidiurnal perturbations that we're observing. And you say, but how is that possible? Coriolis acceleration is causing the modification to the tide. So here's an attempt with a diagram to explain what happened. So with that momentum balance, we're looking at the momentum balance in the cross-shore direction. So remember, there's a standing wave here, and there's something that modifies that standing wave behavior that causes the semidiurnal perturbations. And that, the simulation suggests that that is the Coriolis acceleration. How? Well, if we have a momentum balance in this direction, we have the Coriolis acceleration that's perpendicular to that direction. But that Coriolis acceleration is linked to the surface stress of the wind. Remember when I talked about at the beginning the wind vectors being mostly from the northeast, like this arrow that's drawn right here. So when the wind is from the northeast, that's going to disrupt the standing wave behavior in the South Atlantic Bight. And that disruption will cause this wiggle. Did you see that? The wiggle? If you didn't see it, there it is. Right? So that's how we're proposing that, that the perturbations are being formed. And you said, okay, that's an okay story, but you're not convincing me yet, because it's only one event that you're looking at. So we're starting to look at more events. We went to August 2011, probably you remember that, because it affected New York City, Irene also, very dramatically. And it was sort of similar to Sandy in the sense that the hurricane affected practically all the eastern seaboard of the US, or at least from Cape Cod all the way to South Florida. You see the trajectories were similar in the sense that they started parallel to the coast, and they became divergent later, but they affected the entire eastern seaboard. So when you looked at the surge, at the Homeowner diagram of the surge with Irene, you see the surge very nicely affecting the entire eastern seaboard, but you see the perturbations in the South Atlantic Pipe during Irene. Okay, you say, okay, so there's two, but two is not enough. So that's what we're investigating, and we're looking at more. And I'm going to show you examples of a few, of a couple actually only. There's another from Irene. Irene in 1999. You would have thought that after that one, they would have retired the name, right? But no. Irene is a pesky name, I guess. And here's the surge, the Homeowner diagram of the surge of Irene, and you see the semidiurnal perturbations in the South Atlantic Pipe, the surge in the rest of the domain over there. Then another one was Floyd, and this was in September 1999. And notice the trajectories, they also have in common that they produce strong northeasterly winds here in the South Atlantic Pipe. So Floyd caused the semidiurnal perturbations in the South Atlantic Pipe. You see the surge in the rest of the domain. And then you say, well, those are tropical storms. How about extratropical storms? During this month, not this month, we're in March already. In January of this year, you had a lot of nor'easters, right? So we started looking at extratropical storms also. And this is the surge for the entire month of January of the entire eastern seaboard. Well, not entire eastern seaboard, from Cape Cod to Miami. And what do you see there? Well, obviously in the South Atlantic Pipe, which is from this part on southward, you see all these semidiurnal perturbations caused by nor'easters now, extratropical storms, not necessarily tropical. And also something that we're going to be looking at very soon is that in the mid-Atlantic Pipe, there seems to be some sort of triggering semidiurnal perturbations by these nor'easters. So that's the story, and we're investigating the effects of other tropical storms and more extratropical storms, running more simulations to see whether this mechanism that we're proposing, the Coriolis acceleration, as producing the perturbation holds for other forcing. So in summary, what we have is that surges can get the wiggles, right? And look at it carefully again because, well, it's going to be at the end. But the essence of the mechanism that we're proposing is that Coriolis acceleration perturbs the normal standing wave in the South Atlantic Bight, at least in the South Atlantic Bight. And through the wind stress, the Coriolis accelerations increase, which perturbs the momentum balance like that, and then causes the wiggles. And now look at the main message. Because that's what we found out, and that concludes my presentation.
We take a few questions. So the mechanism that you're proposing is essentially a linear mechanism.
Mm-hmm.
So you could have so you should get should just have a forced response with the wind stress, and then there's the standing wave response, and so those should be completely separable.
Right.
And
Right.
and the forced response you wouldn't think would create these wiggles. I mean, are these wiggles like Kelvin waves propagating along?
No, I think they're forced by the atmospheric forces.
And so but then the time scale of these wiggles, semidiurnal, does that correspond to a time scale that comes from the wind?
The time scale is simply that the tide gets out of phase.
Right, but if it's a linear thing, then the phases of the tide shouldn't interact with the phases of the wind. The only way you can get phase mixing there is from nonlinear.
If you, well, like I showed with the dynamical argument, just by shifting one of the waves and doing the difference between the predicted and the observed, you get these semidiurnal perturbations. So it's simply a phase shift in either one of the waves that cause the standing wave, or both of them. Both of them can get out of phase. And what's interesting is that with the standing wave, you get the peaks in the falling part of the tide, and with a progressive wave, like in eastern England, you get the peak in the ascending part of the wave. So the direct answer to your question is that you can explain this simply with a phase lag. Whether that phase lag is caused linearly or non-linearly, then that's another question, I guess.
So presumably you could, in your model, you could turn on or off the nonlinear reaction.
That's right.
Try that?
Yeah, no, we haven't tried that. But yeah, definitely the effective part can be turned off, or the bottom friction part can be turned off.
But you had your bottom stress was also amplified in that wind tide thing. So that's where your nonlinear effects come in.
Right. Yeah, so bottom stress definitely could cause a phase lag, right? So it can be any of those.
I have a different explanation. The reason why
When done.
the reason why it's occurring there is because of the latitude, because it coincides with the inertial frequency.
Well, the inertial frequency is a little further south
Well,
than there.
But it will be around half. It will be around half a day. So,
Right.
And that's why it does not appear further north. It appears around that region. It's more sympathetic to that area. So I think what the wind does sets up the initial, it could set up the initial.
Right, but that's 24 hours.
Hmm?
That's 24 hours.
That's not 12.
That's,
And we have 12.4 here. It's 24 hours. But what you're thinking about is that why does it appear in the apex of the South Atlantic Backbone? That's where the amplitude of the tide is greater.
yeah, why does it?
So the perturbation will be greater, the greater the original signal is.
Say that again?
The perturbation will be greatest where the tide is greatest. Because that's where if you have a phase lag between the observed and the predicted, the difference
Right.
between the two will cause the
Right.
greatest difference.
Right.
So I think the reason why we're seeing the greatest amplification of the perturbations there is because that's where we have the greatest tidal amplitude, semidiurnal tidal amplitude, to start with. That's where you'll observe it. So if these things happen in the Mid-Atlantic Bight, which is what we're going to explore, at least in the nor'easters, I would expect them to amplify where you have the greatest amplitude in the tide. Does everybody know where the greatest amplitude of the semidiurnal tide is in the Mid-Atlantic Bight? Charlie?
Around New York.
Yeah, so around New Jersey
Yeah.
or New York.
New York.
Okay, yeah, because we think that in northern New Jersey is where we're seeing the greatest semidiurnal perturbations during nor'easter. Here? It's around northern New Jersey. We haven't checked, but maybe it's like you say, New York. Yes, there was.
Yes, two quick questions. First, in terms of storm surge, this would only affect the timing a little bit, but not the magnitude. Is that right? Because that's really
well, as you see, the surge. This is what we're proposing for the forecast. That the surge is not going to be a smooth Gaussian. You need to take into account the phase lag of the tide. And many times these surge predictions don't take into account the interactions with the tides, which we're finding out that are very important. So for forecast, and I think we still need to talk to people at NOAA to see what they think of this idea, but I think that they need to incorporate this tide surge, these interactions of the tides with the atmospheric forcing.
Yeah, but this can be considered as a phase shift.
It is. That's what it is.
Right. It's really a shift in time.
That's right. That's right.
Okay. The second question is, in the calculation, in your linear model, you use the wind stress. Does that wind stress consider the wave pattern of the surface?
In the linear model?
In
no,
the
in
calculation of the...
In the numerical model?
Yeah, the wind stress, does it have this?
The wind stress is the predicted wind, right? So
it does not consider the wavy surface?
No.
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 Flat.
And
Because
also,
it's the...
And also it's so rough at that time, it doesn't really matter. There's no estimation for that.
Okay.
When you go beyond certain speed. We can't estimate the proper speed. It breaks, the channel relationship breaks down.
There's something else?
I have a question. Yeah. I'm wondering how the expression of these kinds of effects would differ over a completely muddy bottom and one that could become fluidized as the system became agitated. So, I mean, you're working on a sandy coastline, sandy shelf, and...
That's right.
And how would it differ if...
Yeah, that's an interesting question. But right now, I would dare to say that since these are very long waves, the bottom type might not have an impact. I don't know. We know that short waves get attenuated in muddy bottoms or fluid bottoms. But tides, I'm not sure whether, does everybody know whether fluid bottoms cause any effects on tides? I don't know. Do you know?
On the tides? No, not so much on the tides, but you're right, on the shorter
waves, right.
Wave
Right.
scale.
So for these long waves, I don't know. My gut feeling right now is that it wouldn't affect, the muddy bottom wouldn't affect the behavior of a long wave. But I don't know.
But you have that coupling with the bottom stress, as Charles was saying.
Right.
That would be.
Yeah, if there's a strong coupling, which we didn't, the simulations didn't suggest that coupling, a strong coupling. If there indeed is a circumstance in which there is a strong coupling, then that's an interesting question to explore actually.
Need a lot of mud. Go to South America.
Right.
Yeah. So the South American case,
Right.
it's the kind of thing, of course you don't get these kinds of storms
Right.
over the muddy coastline of South America so much. But 1,000 years from now, if we still have rivers in North America, our shelf will be muddy. And so these kinds of systems will interact differently.
Right.
Maybe.
Yeah, I think that's a very interesting question to explore.
All right, well, we'll adjourn to the Akubo room. Thank you very much.
Thank you.
Oh, you remember this?
Yeah, that's where the interest
He wants to give you a hard time. 1,000 years from now.
Right.
Are you worried about that?
No, no.
He's up as nice.
He's curious. I'm not worried. Curious.
Very nice to see you. Yeah, my pleasure. To the dean, right? I hear that you're doing a great job.
Oh, thank you.
So,
No, we are very interested in this
I'll be right? In there. 20-some years, right? Oh, a little bit. More with this. Anyway, well, that's a big one. That really is big. I don't know how to
So it all made sense until he used an equation. She's going in the wrong direction. Spring break. It's what spring makers can do.
Red Sea.
Going to see Marcy next?
How are you?
Good. See Marcy next?
I don't think so you're here?
Yeah, well, over on the real.
Real? What department?
Technology, society. Sheldon and I all
Right.
They have pizza.
It's good to see you.
Right, see you there.
They have pizza, but they won't open it up until you
And as I said, it made great sense until you wrote the first equation. Then I lost it. So that was
Yeah,
all
because you didn't want to listen.
Arithmetic was my best time in math.
No, but the wiggly line.
The wiggle, oh, yeah.
Wake up.
That's really good. Yeah.